All right, we are going to be talking tonight for a few minutes about coordinate plane geometry, so to speak. That is, how do we walk our way around plotting points on a coordinate plane? Some of you will remember this quite well, I think, from previous coursework. And then we're going to extend that somewhat and talk some about whether a certain point is a solution to any given equation. We're going to talk some about calculating slope of a line, and then we're going to actually do a few word problem applications of some of these ideas. All of that is just 8-0, and then for 8-1 and 8-2 tonight, we move on into some actual work with measurements of angles and working some with plane figures. So rectangles, polygons, some other things. So that's where we're headed. I'm thinking that this recording may be a little shorter than some of the others have been. Let's start by plotting pairs on the coordinate plane. So you probably remember that if you saw something like that, two numbers separated by a comma inside these little parentheses, you remember that that means that the x value I'm looking at is a 2, the y value I'm looking at is a 5, and that if I consider this to be the 0, 0 point, kind of the starting point for both x and y directions, then I could count out and plot that 2, 5 point by counting 1, 2 in the x direction and 1, 2, 3, 4, 5 in the y direction. Right, and there it is. So many of you, again, I think will remember how these go. We'll do a few more, but I won't spend a lot of time with this. So maybe I have a point at 4, -4. That says I need to count 1, 2, 3, 4 forward in the x direction, and then 1, 2, 3, 4 down in the y direction. The -4 means all my negative y values are down here below the x-axis. So that point would be there at 4, -4. How about the point? So you should try this one with me. Try this one yourselves as well. So the point -3, -7. Wouldn't that have to be starting here at the origin, counting back 3 in the x direction, and then down 7 in the y direction, right? So note here that both the x and the y coordinate for that point are negative. Right here, both are positive. Here, the x is positive, the y is negative. And so finally, if I had a point that had a negative x and a positive y, that says from the origin, I would be counting 1, 2, 3, 4, 5 negatively in the x direction, 1, 2, 3, 4 positively in the y direction. And that point is at -5, 4. So I'd like to, if I had you in front of me, I'd be asking you how many of you remember all that. I'm going to assume, though, that many of you will remember a good bit of that. You should also be able to work in the other direction. So that is, if you see a point, oops. So this is that thing that happens with the controls here. Pardon that bumping, just as well that we moved that. I was ready to. So if you had seen a point sitting somewhere on the plane, you should be able to name the point. So for example, here, seeing that point there, I would say, well, to get to it from the origin, I would have had to count back 3 So in the X direction, it's a -3, and then I would have had to count up 3. So it's the point -3, 3. So I'll give you a moment to try a couple of these. Identify that point. And that one. And this one down here. All right, so I'd like you, please, to let me know how much of this you remember by identifying those 3 points, and then you can take a picture of this in your notes. Take a picture of what I have looped. This will be for you guys, will be a day 8, number 1 in class activity to turn in. So your job is to name the 3 unidentified points. Take a picture of that, turn it into the day 8 activity assignment. And be on the lookout. There may be some other problems to turn in through the course of the lecture as well. So we have in the next couple of slides, there's just room for more practice there. So I think we'll keep moving out here to our first real problem. Make a vertical table of solutions for this equation. You remember, again, how this goes, that we sometimes in a previous class had to set out this XY table and fill in what these numbers should be based on the equation. So if the X is here, we're asked to use our -9, -3, 0, and 9. The question then is, what Y's do I get when I put those in? So putting in the -9, we'd see a -6/3 in the top, -2, right? Putting in the -3, I get a 0 in the top. 0 divided by 3 is just 0. Putting in a 0, I get 3/3, which is 1. Putting in a 9, I get 12/3, which is 4. And furthermore, the page doesn't outright ask us to do it, but while we're here, we might as well practice this. And that is, we could plot these on the coordinate plane. Go ahead and do that. So I'm going to sketch this somewhat roughly. 1, 2, 3, 4, 6, 7, 8, 9, 10. I guess it could steal this from another side too. 4, 5, 6, 7, 8, 9, 10. But this will do. 1, 2, 3, 4, 6, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. So -9, 2 looks like it would be right about here. -3, 0 is right here. 0, 1. It's off there. Right there. 9, 4. 1, 2, 3, 4, about here. I don't like that -9, -2. Let me look at that again. So -9 plus 3, -6/3, -2. Oh, -2. All right, so hopefully you spotted. So yeah, so here's a good teaching moment for all of us. So what I'm thinking about is the fact that my algebra insight tells me I should expect a straight line here. I can see that I would have a straight line through these 3 points. Something is off about that other one, right? Which says then, oops. In other words, that's sort of the idea that I was looking for a line is a bit of a check on my points. And maybe you caught it when I flew through that -9, -2 is definitely not here, right? This is the wrong point. That's the error. So if you were catching that, good job. -9, -2 would be right about there. And again, what's interesting about this is simply the fact that this forms a straight line, and I knew it was going to because you'll remember possibly something about your algebra. Remember that y equals mx plus b form of the line. And you might think, well, that doesn't look like a y equals mx plus b, but it actually is, because that divisor of 3, I can apply to each part of the fraction. In other words, I'd have a multiplier of 1/3 for the x, 1/3 x plus, and then 3/3 1, which says, remember how that goes, it says, first of all, this will be a straight line if you're looking at something that has that form, mx plus b form, something multiplying your x and then some other value added on at the end. It's going to make a straight line. The 1 is always the y-intercept, so that's consistent. The slope of 1/3, I'll go ahead and look at slope idea while we're at it. So slope of 1/3, maybe you remember here, says I can tell how tilted the line is and in what direction based on the slope. The slope here, for example, from this point to this point, says if I count up 1 and forward 1, 2, 3, I'll land on the line. And if I do it again, I'll land on the line again. Up 1, forward 1, 2, 3. You can see this again is approximate because of the sketch. But up 1, forward 3, I would land on the line. And I can keep repeating that. That's what defines this as a straight line. Up 1, forward 1, 2, 3, more or less. And there it is again. So the slope is, again, a number that defines how tilted is the line, how tilted, and in what direction. In other words, this is a fairly flat line. It's not like this, right? It doesn't have that kind of steepness to it. And it's also a positive slope. This is a positive slope. 1/3 is a positive number. All positive slopes have that sort of a lean. All of those would have a positive slope, while a negative slope, maybe you'll remember this, a negative slope kind of has what I think of as a backward lean. All negative slopes look like that. Okay, and therefore, I can see graphically that the 1/3 slope shows up here. But you remember also that we have a slope calculation. Maybe you'll remember that. And this is actually coming up in the coming slides. So we're just sort of talking about it here while we're playing around with this. And the slope calculation basically says, if I have 2 points, I can look at the difference in 2 y's, divide that by the difference in the 2 x's, and I should be able to see the slope of that line. So I could show, for example, if I pick the 2 points, -9, -2, and -3, 0, I'll just pick those first 2 in the list. It does not matter whether I call, which point I call 1 and 2. So maybe I'll just do the obvious and say this is point 1. So there's x1, y1, here's x2, y2. So maybe you remember this, the y2 minus the y1 here would be 0 minus -2. The x2 minus the x1 would be a -3 minus -9. Be careful because this minus belongs to the formula and the other minus belongs to the number. So you do have those two negatives. So we have 0 plus 2 in the top, and in the bottom we have 9 minus 3, 6, 2/6, which is 1/3, which is, in fact, the slope that we saw just by looking at the equation. So there's a quick reminder about slope as a calculation, and as you see it on a graph. We'll practice that a bit more as the slides continue here. So here, though, is another idea to think about to tell whether or not a given point is a solution. Determine whether a given point is a solution to a linear equation in two variables. In other words, if we saw this statement, 3x plus 2y is equal to 7, does 0, 4, if I put in 0, 4, do I get a true statement? If I put in 1, 2, do I get a true statement? And so on. So we try it out. The 0 is the x, the 4 is the y. So 3 times 0 is just a 0, plus 2 times 4 would be 8. That's not equal to 7. All right, 2 times 4 for the 8, that's not 7 at all. So this is a no. This point's not a solution. It's not a point that would show up on that line if we looked at that on a graph. So we try another one. 1, 2. 3 times 1 is 3, plus 2 times 2 is 4. That definitely does equal 7. Therefore, this is a point on the line. Okay. Negative 2, 1. So 3 times negative 2, negative 6, plus 2 times 1, 2. This also failed. Stylus is kind of clunky, so it's very hard to write small. It's hard to write neatly, apologize. But negative 6 plus the 2, this is a no. This is a fail. And negative 1, 5. How about that? So 3 times negative 1, negative 3. 2 times 5, 10. 10 minus 3 is 7. So this is also a yes. So we were able to test whether or not a point is part of a solution to a line, given just given point, putting it in. So here, I would like you guys to do this one. So this will be an activity number 2. So in class activity, this will be your day 8, number 2. So you'll come through and try out each of the points. And if you write it out, that's fine. If you can kind of do it mentally, you know, and keep track, that's fine. But what I want to see is, like I've done above, either a yes or a no above, below each question. I'm sorry, below each point. Either a yes or no below each point. That would be sufficient. Okay, so I'll let you, if you need to, pause this, complete that. Take a picture of it and be ready to turn that in by the time all of this is done today. Okay. So I really would like to be able to say how many of you remember this. So I'll try to get a feel for that when we get back in class next time here on day 9. Make a table of solutions for the equation x minus y is equal to 6, and then use the table to graph the equation. So this says, again, figure out some x's and y's that work. To make a graph here, you might need 3, 4, 5 points. You know, you want at least 3, but several is needed. And so I could put some points in here, say, what if I put in a 10? Then what would I have to subtract to make that equal 6? 10 minus, so y would have to be a 4, right? If I put in, say, let's do something interesting. How about if I put in a negative 2, x equal to negative 2, what would y have to be? So thinking about negative 2 minus y equal to 6. So with a little thought, maybe you've already looked at it. If I put in a negative 8, I get a negative 2 minus a negative 8 is equal to 6. And I just found that by just kind of looking at it, thinking about it. I didn't especially do any, you know, swapping things around and move things in any way. I just thought about it. What if I put in a 0? 0 minus negative 6, right? It has to be negative 6. 0 minus negative 6, because minus negative 6 is a positive 6. So that has to be a negative 6. Strange. And then maybe we'll put in one more. So 5. How about 5? Well, 5 minus negative 1 has to be the 6. 5 minus negative 1 would make 6. So I've done the first piece of this. I've made the table of solutions. Now I'm going to use it to make a graph by plotting those points. 10, 4 would be 1, 2, 4, 5, 6, 10, 4 right there. Negative 2, 8. Negative 2, 8. Negative 2, 8 right there. Thought I was going to put it in the wrong place again, didn't you? I saw what you were thinking. Got me back in the right direction. Wait, it's negative 8. Hello, I'm not even paying attention. Let's try that again. Negative 2, negative 8. Get it right. Negative 2, negative 8. Okay, that's good. 0, negative 6. So 1, 2, 6 right there. And 5, negative 1. So 1, 2, 3, 4, 5 in the x direction, down 1 in y direction. And once you've got the points, it's a good idea to go ahead and connect them, see what's going on. Get a look at the line. You can see here, of course, that the points do form a straight line. We could also take a look at the slope if we wanted to. You can count out the slope from point to point. You know, you can see that there's actually a point for each intersection here, and the slope is up 1 over 1, up 1 over 1, up 1 over 1. So we have slope of 1. The slope is equal to 1 here. And we could also, if we wanted to, we could kind of manipulate the equation to see that happen. X minus y is equal to 6 is what we were given. But what if I said, well, my goal would be to get a y equals mx plus b form of that line. Can I swap things around so that I see y by itself? And I certainly can do that. I could add y to both sides. I could bring these 6 over. So I could write this as x minus 6, and then moving the negative y over means that this will be the positive y. So I can get that y equals mx plus b form of the line just by swapping things around a little bit. Move the 6, move the y. When I do that, I can see a couple of things, which is consistent with what I have already discovered. I can see that I have a y-intercept at negative 6, which is right there. That's that blue point, which we saw over here at 0, negative 6. I can also see that my slope is 1. There's an invisible 1, right, sitting in front of that x. 1 times x is x. So I do have a slope of 1 showing up in my mx plus b line, which is, again, consistent with what we've already seen. Okay, so hoping all of that is kind of bringing some refreshing back to you. I'm sure that you've seen these things and maybe this is coming back to you pretty easily. And furthermore, if I really wanted to extend the look at this just for the practice, I could go ahead and just try that slope calculation again. So I'm going to do that for your sake, to review that slope calculation itself. And to do that, I need a couple of points. So I'm going to pull off arbitrarily, a couple of my points. And my slope calculation will be the difference in the y's, negative 8 minus 4, divided by the difference in the x's, negative 2 minus 10. And so we'll look at what I get. Negative 12 in the top, negative 12 in the bottom. Oops, got too many lines there. Negative 12 in the bottom, which amounts to 1. The slope is 1, which is consistent, again, with what we saw on the graph and by rearranging the equation. All right, so we'll clear that. You have, again, several other slides there in your notes that were intended to continue to practice that in class as needed. So I think what I'll do here is give you a couple of points and let you try the slope calculation and just turn that in for me. So here are some points to work with. I don't know what that slope will come out to be. Don't forget, there's no reason it has to be a whole number. It could be a fraction. So I would like you guys to calculate slope for these 2 points, y2 minus y1 over x2 minus x1. So get the calculation done and then turn it in class activity day 8. I'm giving you a lot to do today because I'm assuming that much of this will be review, and therefore it's not so much that you need a lot of instruction from me as a chance to practice and show me what you remember. So I'll let you complete that one for something to turn in. And as always, if you get stuck on something, please let me know. When we meet up again in class, or you can always email as well if you don't want to wait that long. All right, so we'll let you finish that out. That turned in, and let's look at a couple of word problems. So write an equation that models the described quantity. Specify what each variable represents. Worker has already earned $300 and is being paid $13 per hour. So if I were to ask you some questions about this, if I said to you, well, how many hours did the guy work? How many hours did the guy work? You'd look at me and say, well, I don't know. So since we don't know, I don't know, it means it's a variable, right? If you have an answer to that question, it's like, I don't know. Well, it depends, right? Then it's a variable. So we'll say that X is going to be the number of hours that the person has worked, okay? Number of hours worked. And if I said to you as well, how much did he make? What was his total? How much did he make? And again, you might say, well, I don't know. Then that can be Y. Say that's Y. Total money. And I'm saying total, so be sure you're clear on that total money. So what could I do if I wanted to write an equation that shows this situation? Wouldn't I have to say that his total money, which I've said is going to be Y, wouldn't I have to say that his total money is going to be the $300 he's already made plus his $13 per hour times some number of hours that we don't know yet. And if I write that, then if you gave me a number of hours, I could give you the total, right? If you said, well, okay, I'm going to see if I can stump you. He worked 13 hours. What would you do with that? Well, you put the 13 in, right? And you'd be able to find out what the Y is. 13 times 13 happens to be 169. 13 times the 13 hours, 169, which says then he would at that point have had made a total of 469. Oops, can't write it. $469. So we've written an equation that would allow us at any given number of hours worked to predict how much money he made. Okay, that's how we do that. And so there's one similar to that here. on the next slide, it is very much the same. The story is a little different. Carpenter's already shingled, right? Already shingled 5 garage roofs. And he's now shingling roofs at a constant rate of 7 per day. So once again, if I said to you, well, how many days has he been working? You'd say, I don't know. So isn't that a variable? Number of days he's worked. In other words, has he worked 5 days? Has he worked 30 days? We don't know. But we could find out what the total number of roofs was. If we knew the number of days he worked, we could find out a total, right? So if I said, well, how many has he done then? How many total has he done? You'd say, I don't know. So that's the total number of roofs done. Total number of roofs. In other words, again, if I know the number of days the person has worked, I could tell you what the total number of roofs is. So your job is, again, here to do this part, write the equation. So you're going to write that equation and then turn that in for me. So we'll have a lot of these little activities. They're all fairly small, but a lot of these today, because again, I think that this is work that you have seen before and that I'm assuming is largely review, and that what you need is the chance to practice a bit. So this is in-class activity day 8, number 4, to write the equation that shows this situation. Right, so we need to do that. And again, of course, you can always stop the recording and, work on that a bit and then start again. So I'll leave you to do that. We have a couple more that are interesting here to think about. Here, this is a little bit different from the previous two because those two were building up something. The guy was adding each day the number of roofs that he completed. The worker was adding each day, increasing the number of dollars total that he had been paid. Here we have a barrel. It has 142 gallons of gasoline in it, but it's being drained at a constant rate of 10 gallons per minute. So, common sense says, well, you're subtracting the number of gallons, per minute. It's going to bring this down, right? The thing is being drained out. So once again, if I said to you, well, how many minutes has the draining been going on? You'd say, I don't know. So could we say that X should be the number of minutes this operation has been underway? Has it been 10 minutes? Has it been 2 minutes? Has it been 3 days? Who knows, right? Number of minutes it's been going on. And could I also say, could I ask you a question? Well, then how many gallons are still in there? How many gallons are still in there? And would you say, I don't know. So wouldn't that also be not only the Y, we could identify it as Y, but we would realize that the number of gallons that's still in there depends on the number of minutes that have passed. Y is what we call the dependent variable because whatever number of gallons is in there depends on the number of minutes that have been passed. Number of gallons still in the tank. How much is left in there? I don't know. It depends, right? If you kind of have an answer in your mind that way, it means that X is what we call the independent or input variable. Y is what we call the dependent variable. The Y situation is a result of what happens in X. The number of gallons is a result of the number of minutes that have passed. So, having said all that, what do we want to say here? Wouldn't we have to say that we started at 142 gallons? We started at 142 and we were subtracting off some number of gallons. And the number of gallons that we're subtracting is 10 gallons per minute times the number of minutes. Okay, so here what we see is essentially a sort of a negative slope idea, right? Anytime you see a quantity decreasing over time, then you're really thinking about a negative slope. And you can kind of check to see if this makes sense. You know, if you say, well, okay, I'm just going to put in some numbers and sort of see what it looks like. If I put in, say, 3, x equal to 3, that means I've drained out 30 gallons, right? It means I have 142 minus 10 times 3, 30. So I can tell you, again, I could tell you the number of gallons that are still in the tank, 112. Right? All right. So negative slope, something to think a little harder about. It means that you're losing something. As time goes on, you're losing something. And that is useful for us in the next couple of situations that we're looking at. So here's a little sort of a playful idea for how to talk about the shape of a graph that models the situation the best. If you have $1,000 savings and you have maybe you looked at the market, which is getting like what, 1%, 2% interest, almost nothing. So your savings are really not doing much in any standard savings vehicle, you know, an IRA or certainly not a savings account at the bank, CDs, nothing is really building much of any real income right now. So putting $1,000 savings under your mattress for a year is not a whole lot different from putting it in some savings vehicle. Not a whole lot different, sadly. So, so you put $1,000 under your mattress. So maybe my scale here is such that every, 1, 2, 3 is thousands of dollars, maybe. So if I have $1,000 and I put it under my mattress for a year, well, after the first day, I have $1,000. After the second day, I have $1,000. Third day, I have $1,000. It's never going to change, right? This would be, the graph of this would have to be a flat line that is just a constant. It's not, it doesn't increase, it doesn't decrease. It's just going to stay level at $1,000 no matter how much time passes. And in fact, if you really wanted to bear down on that idea, wouldn't it make sense to say that it has a slope of 0? How much does it tilt? Not at all. That's what we're asking when we talk about slope. How much does the line tilt? It doesn't tilt. It's flat. Sadly. So here's another scenario. What about the shape of the graph that would model a beginning weight of 200 pounds and a loss of 100 pounds per month? You'll find that if you get information that says, well, here's something that happened at the beginning. He'd already done 5 roofs. He used to weigh 200 pounds. There were 142 gallons in the tank. You got some beginning situation that's going to always end up being your y-intercept. So, and again, what we're doing is thinking about the slopes really. But if I have a beginning value of 200 pounds, again, I could sort of scale that on my graph here. Maybe each of these is like 40 pounds. So I could scale that so it would fit. You know, that's all I'm doing. 40, 80. This doesn't want to work very well. 120. So 40 more, 160. 40 more, 200. So I'm trying to put this so it'll fit on the graph. So 200 pounds, it's a beginning weight right here. But I'm losing, but somebody's losing 10 pounds per month. Losing 10 pounds per month. So that says, as time goes forward, the pounds is dropping, right? As time goes forward, pounds is dropping, which says that I started at 200, but I'm going to have a negative slope. This will not be the correct slope because, again, it doesn't want to, I'm not trying to graph this in a real specific way, but I do want to say that the slope would be negative as I go forward in my time, in my x direction, my weight values, the pounds, are dropping. I get that slant that sort of as a kind of leaning back look to it. I could also write the equation for this because the loss of 10 pounds per month it's exactly like the tank of gasoline. 200 pounds minus 10 pounds per month. If X is the number of months, if X is the number of months and Y is the total pounds, this would be the equation for it. And here we see again a negative slope, negative slope. Compare that to the next one. What is the shape of the graph that best models the average cost of a new car over the past 10 years? So this is not giving us specific data. It's just giving us a little scenario. But we know from life experience, we know a little bit about this. We expect that the cost of a new car is increasing every year, right? It might start at, I don't know, how much does a new car cost? I've never bought a new car. I have no idea. Not even a clue. I suppose a very, very cheap new car might be $20,000. If you're laughing, you could buy a wagon for that. I don't know. But I would say if that's sort of my starting point, my time equal to 0, I would say that I have enough sense to know that the cost of that car is increasing over time. So my slope here, I would expect to be a positive number. The slope is increasing, and that graph would indicate that again, the cost is increasing over time. Simply because it's a part of inflation like everything else, right? There's always a little bit of inflation. Sometimes there's a lot, like right now. Okay, so we've got one more word problem to think about that really pulls in these ideas that we've just been talking about, starting points and the meaning of slopes and so on. The traveling ant. You have an extra slide, an extra space in your notes in the following little spot there for a place to try to answer some of this. So the question said, suppose that y is equal to negative 3x plus 18. Suppose that's graphed on an xy plane where the x-axis is time in minutes. The y-axis is distance in feet. If this graph represents the distance that an ant is from a stone after X minutes, answer each of the following. Is the ant moving toward or away from the stone? Initially, how far from the stone is the ant? At what rate is the ant moving? And at what value of x, at what time in minutes, will the ant be at the stone? So what I'm going to do is give you kind of a couple of broad strokes here and set you loose to try this one and turn it in. Okay. Is the ant moving toward or away from the stone? If you were to graph this first, it might be a help to you. You've got some space to do that on the next page. But I would ask you to just consider what that negative slope is telling us in terms of distance. In terms of distance from the stone. Is the distance from the stone decreasing or increasing? Is the ant's distance from the stone, based on that slope, would you say that the ant's distance from the stone is decreasing or increasing? If it's decreasing, the ant is moving toward the stone, right? If the distance is decreasing, the ant is moving toward the stone. If the distance is increasing, the ant is moving away from the stone. If the distance from the stone is increasing, that distance is getting longer, the ant is moving away from the stone. So you decide which one it is. Initially, how far from the stone is the ant? We spoke a minute ago about the fact that at time equal to 0, at any starting point, whenever you talk about the beginning of something, you're talking about a y-intercept. The beginning of something will be a value on the x-axis, where time is equal to 0, nothing has happened yet, right? At time equal to 0, nothing has happened yet. So the beginning of a situation will always be reflected as a point on the y-axis, a y-intercept. At what rate is the ant moving? Well, remember, we've already got the units and so on stated here. We've got essentially feet per minute, because those are the units that we're working in. The feet unit is the distance, time unit is minutes. So in some feet per minute, that ant is moving. What would that speed be based on the equation? What is the feet per minute based on the equation? And when does the ant, at what time that is, when does the ant reach the stone? That is, if the ant has reached the stone, then the distance between the ant and the stone is 0, isn't it? The distance between the ant and the stone is equal to 0 if the ant has reached the stone. So this is asking, when is that y? Because the y is distance. When is the y? When will that y become 0? When will the y become 0? At what x will that y value have to be 0? So you have some space there on the next page. So I would again ask you to, I'm going to clear this and ask you, of course, you can always reboot the video, go back a few seconds if you need to see something further. But I'm going to ask you to answer all of those. And I'm going to suggest that you do that on the space that's sitting there on that blank slide on that next page. It's just below, this one for you and your notes. So you've got some space there to work. Show the graph and list out A, B, C, and D and give your answers on that space that's on the next slide shown on your notes there. And then turn that in for me as well. So in class activity day 8, what are we on, number 5? So giving you, again, a lot to do in this section because I believe that it's generally review for you. All right. I'm going to close this one and bring up 8181. Okay, 81, angle measurements. Angles are measured by degrees. Angles are measured by degrees. I think you would probably know that already. You probably are already thinking that a circle, a whole circle, contains 360 degrees. That makes a quarter circle or a right angle equal to 90 degrees. And it may also not be, well, I don't know whether to anticipate that you were aware of this piece or not, but we can further divide a degree into smaller units. We can divide it into minutes, and we could even divide the minutes into seconds. Most trade work requires precision only to the nearest degree, but there could be times when you need to have something more specific than a degree measure. And so the way that works is that each degree is equal to what we call 60 minutes. That is, it's not time minutes, but we're taking a degree, a single degree, whatever that would be, a single degree, and thinking that is divided into 60 tiny units, 60 units. So 60 minutes, we would write that this way. If you should ever need to know or work with this, 60 seconds is in 1 minute, and we write that this way. But for this coursework, I think that most of the problems you'll see don't go any further than in degrees and minutes. We've got a little review about how to use a protractor. I'm hoping that this is simply, again, review for you, so I'm not going to spend a lot of time on that, but I'll just remind you that if you're looking to measure, for example, the angle that sits right here, which we would call angle EOD, something like that, if we wanted to label it. That to measure that, we would want to line up a center mark on the protractor with the vertex of the angle. And from there, since this angle is less than 90 degrees, we would be measuring on the smaller scale. We'd say that's a 60-degree angle. Angle C straight up and down is a 90-degree angle. And then over here with this angle AOB, angle AB or AOB, here, let's see, let's look at this way. Switch what I was going to say. Angle EOB, that one, let's talk about that. That one is larger than 90, larger than 90. And that tells me then that I'm going to need to look at the scale where the numbers are larger than 90. I can't use the 40 and the 50. It's not a 45-degree angle. It's actually going to be halfway between 130 and 140, so 135. So again, if there is some question about using the protractor, you can let me know. We'll work on that. But I think that you've seen those before. So this is what we just did. Angles come in classifications. You can kind of group angles together in a couple of ways. One is by talking about the angles themselves. So a tight angle, less than 90 degrees, we say is an acute angle. You may have heard acute little angle. Anything less than 90 degrees is acute. Anything greater than 90, but less than 180 is obtuse, obtuse. Stop that to spare you sneeze. And then you probably as well remember that a right angle is an angle that's exactly equal to 90. And the lines then meet at what we call a perpendicular. Perpendicular lines meet at 90 degrees. You might be surprised to know that this is an angle. Oh, let's fix this. Screen sharing, stop it. Showing. Oh, that's a previous message. Okay. Okay. So you might be surprised to know that this is an angle. It is called a straight angle for obvious reasons, but it actually has some degrees to it. And you might think, well, how is that possible? It's just lying there. You know, there's nothing going on. But it's half of a circle. So it's half of the 360. That angle is 180 degree angle. Straight angle is 180 degree angle. Strange but true. We have certain ideas that are helpful as we start to see angles sort of compared to one another. If we see two straight lines intersecting like this, we know that opposite angles are equal. B and D here would be equal to each other. And furthermore, A and C also equal to each other. And there's another idea here as well. Go ahead and look at, and that is if my two angles are on, two angles are on a straight line. If my two angles are on a straight line, for example, the angles A and B, don't those two angles together have to add up to 180? And we call those complementary angles. Supplementary, actually, is the word supplementary. The idea is not, the word isn't the critical idea. The idea is just to realize that, again, the two angles on a straight line have to add together to make 180. So we've got several 180 pairs here. We've got A and B, but we've also got B and C. Those two add up to 180, don't they? Right? We also have D and C. Those two add up to 180 because they're on a straight line. And we've also got A and D. So I actually have four pairs of what we call supplementary angles that add up to 180 here. Okay, so those are helpful ideas. Just talked about that here. So, and furthermore, we have information understanding that all triangles contain 180 degrees, which says then that if I know two angles in a triangle, if I happen to know that one is 69, for example, and maybe I know that one is 36, this is not necessarily to scale. One is 36. Actually, I was trying to do that by the way that's stated up there, so it's not confusing. So I gave A to B the 69. So the C will say 75 because that's what it says up there. All right, so if I know that, then I could take those two and subtract them from the 180 total, and I would be able to name the measure of the last angle as 36. So if I know two, I can find the third one because the total always has to be 180. All right. Let's talk about there. So, let's talk about this one. The first one's kind of on a simple one, kind of obvious what we just did. But this one involves degrees and minutes. If I know that angle P is 27 degrees and 42 minutes and angle Q 76 degrees, 25 minutes, what about angle R? Well, that suggests that first thing I probably need to think about doing is to go ahead and add together the two known angles. including their minutes, right? So when I add together those minutes, here's what's interesting about that is I get 67 minutes over here in the degrees, 103 degrees, but I have 67 minutes, which says then, what couldn't I take out from that 67 minutes? Couldn't I take out 60 of the minutes and call that a single degree and add that in to the 103? Actually, I have then 104 degrees, and 67 minus the 60 leaves me 7 minutes. So it's like taking, you know, enough nickels and dimes and turning it into a dollar. We're taking out 60 minutes, calling it 1 degree, adding that in to the 103, and then the remaining minutes is at 7. And at that point, then I could go ahead and find my angle R if I can subtract that 104 and 7 minutes from the 180. But think about this. You've seen things like this before where there's not minutes to subtract from. How am I going to do that? There aren't any minutes up there. So I actually have to restate the minutes out of 180. I could take out a degree, take out 1 degree, and call it what? Right. So if we were in class, you'd be telling me I should call it 60 minutes. 179 degrees and 60 minutes is the same as 180 degrees. But now I have minutes that I can subtract from. So I can take that 7 minutes out of the 60 minutes and say I have 53 minutes there. And in terms of the degrees, I have 179 minus the 104. So 75 degrees, 53 minutes would be angle R. You may see something like that in your travels in the homework where you have to break up minutes into, or you have to move minutes into a full number of degrees, and or you may have to break out a degree into minutes in order to get a subtraction done. Another important idea regarding angle measure is the idea of angles that are formed from parallel lines. If I take parallel lines and I cut across those with some other straight line, we call these, there's a whole bunch of equal relationships in here. You see the text here referring to corresponding angles and alternate interior angles. The main thing is kind of understanding how these work. It's not real critical that you remember all the names. But suppose I said that right here, I have a 100-degree angle. Knowing what you know already, for example, knowing the angles that sit on a straight line have to total 180. Wouldn't you know that this is 80 degrees? And if this angle right here is 80 degrees, this angle down here, this is the corresponding angle. This is the idea of the corresponding angle. The corresponding angle will also be 80 degrees because you've got the same relationship between the red line and the blue line. What the red line and the blue line do up here is identical to what they'll do down here. So those are called corresponding angles. And so you can see that quickly we would know every angle in the diagram. This is corresponding to the other 100, but you would also be able to say, well, it's all the 180 that sits on that straight angle. We know that this has to be 80 We know it in two ways. We know that again here, this has to be a total of 180 sitting on that straight line, but we would also know that it's 80 based on the fact that these are opposite angles across that intersection. A, B, C, D, the A and the C will be equal. So we'd see that there. So there's all kinds of ways to get at this information, and we could know all the angles in the diagram very quickly. Again, this one has to be 100, this one has to be 80, this one has to be 100. So I'm going to clear that and then give you guys a chance to try this. I'll make some different numbers. I'll just take these out. It's the same drawing. Please realize that I'm not necessarily trying to make this to scale, so that the numbers I give may or may not, you know, be close to what they really look like there. That's okay. Doesn't have to look exactly right. Just take it for granted that something is okay about that. So I'm going to say, what if this angle is 43 degrees? Let's make that, again, it's not really very close. I'll make it so it's a little more reasonable. What if this angle were 73? It's closer. 73 degrees. What if that angle is 73 degrees? And you guys, again, please fill in what's missing. A8, so this will be number 6, problem number 6. So you finish what's missing here. Realize that I would be asking you in class to do these. So really, again, we're trying to replicate the experience that you would have if we were face to face, because I'd be asking you in class to do this. So that's what we're doing here, just making it as much like being in class as we can. So complete the missing angles there, and make sure as you turn that in that you have it looped in the way I have it looped, and labeled in the way I have it labeled in class activity day 8, number 6. All right, and I'll leave you, you can again stop the recording if you need to, so I'll leave you to finish that out. And finally, then we have an interesting word problem. We have a plumber who's connecting two vertical sections of pipe. So the two vertical sections here and here, he's connecting those. They're not standing close to each other. So he has to connect those with an angle piece here, 30-degree elbow piece. That is this angle A here, right here. The angle A is 30 degrees, right here. So the question is, what angle does the elbow make with the pipe above, right here? If this is a 30-degree angle here, what is this angle? So there's a couple of ways we could think about this one. One way that might be possibly most helpful would be, I'm trying to get the lines to look a little nicer for you, would be if I pull off that triangle and just sort of redraw it so I can see better, think about it a little better, think about what's going on, get a little more information in front of me. This was the 30-degree angle. This has to be a right angle, you know, right there where the pipe perpendicular would come down that center line. In other words, we're considering that to be a right angle, has to be. So there's a right angle there. And that means that here I have 30, 90, 120, which means this is a 60. This is a 60-degree angle. So right here, this is 60. That's a 60-degree angle. And isn't that on a straight line? Isn't that a straight line angle such that if I know that this one is 60, doesn't that automatically tell me that that next one has to be, and I'm hoping you're saying 120, right? This one has to be 120 because it's on a straight angle with the 60-degree angle. And we knew the 60 because we knew that that had to be what was left if this is 30 and 90. You might have spotted other ways to think that one through, but and if you got the same result, then that would be valid, whatever your process was. Okay, so that's 8-1. I'm going to get this knocked out and pull up 8-2. Last thing we need to do tonight. All right, and so you're seeing perimeter of polygons, an area of quadrilaterals. We need to identify polygons, find area and perimeter of geometric figures, solve some practical problems involving area and perimeter. So polygon sounds like an exotic name for something, but it really is just a general name for a figure made of straight sides. It just means many sides, many straight sides. So these are all polygons. It's just a general name. This is a polygon. This is a polygon. Just means it's made up of straight sides. These are not polygons because the sides are not straight, or there aren't any sides. So perimeter of a polygon, perimeter is just distance around the outside. So perimeter just means that we're going to add up the side lengths. That's all that is. I'm not sure why students seem to be very puzzled sometimes about perimeter. All it is the outside distances. It's the length around the sides. That's all it is. So we add those up. So here's an interesting question, though, word problem. What's the cost then of fencing a rectangular playground that measures 45 yards by 58 yards at a cost of $16 per foot? I'll make a better line there. All right. So the first thing that you might be careful about here is realizing, and of course you should make the sketch. You absolutely should make a drawing. Yes, you should make a drawing. 58 yards. So the first thing to think about is, again, that if we're fencing something, then are we talking about area or are we talking about perimeter? Well, we have to be talking about the distance around the playground, right? This is perimeter, the distance around the playground. This distance, this is the fence, right? So it's a matter of adding up all that distance. You'd have what? 45 and 45 is 90 plus what? 116? 58 and 58. So it's not a big jump to say that we have 206 yards to cover. But when I go down here then and start trying to answer my question, because I'm interested in the cost, right? So I've got to take the 206 yards and somehow convert it to this dollars, convert it to the cost. But look at what I have. I'm in yards, and this stuff sells per foot, which means I have to get out of yards and into feet. I can do that with a unit multiplier because, again, there's no possible confusion about whether I should be adding or subtracting if I will use my unit multiplier. I'd like to get out of yards, so I put yards in the bottom. I'd like to get into feet, so feet goes to the top. And I know that that relationship is that 1 yard is equal to 3 feet. Again, this is a fraction equal to 1, therefore it's a pairs multiplier. Nobody will put me in math jail. So I don't have to sit here and sort of double second guess myself. It's the word I want. Second guess myself about whether I should multiply or divide. You might think in this case it's very simple, and why would you even, how would you even ever make that mistake? But you'll find that if the units are not familiar, if the units are not familiar, then it can be very, or if you have a string of conversions, 5 or 6 conversions that you're having to do at one time for one problem, it can be confusing about whether you're multiplying or dividing, and it's a good idea to practice using this unit multiplier thing. It will get you out of every single confusing situation that you might encounter in terms of these conversions. So I have here 618 feet, right? 618. So at that point, then I'm ready to think about my cost. I have 618 feet. And again, times, here's my unit multiplier again, times $16 for 1 foot. Feet is what I want to get out of. I want to get into the dollars. I can see clearly that I have to multiply. You might think that this, again, in this case, was not necessary, but the point is to be able to do this when you are not certain that you are clear on whether you're multiplying or dividing. You'll see some examples of that as we do more and more of this. So we would be saying then that this is a cost of $9,888. Hopefully you saw that coming. And let's do some more. Some of these, you know, as you can see, I did that one for you, so to speak. And some of these I'll ask you to work out your own. So here's an interesting little scenario. First of all, thinking about area of a rectangle, we're looking for rectangle areas and finding missing dimensions. How do we do that? So area of a rectangle, we know, is length multiplied by width, just to remind you. And so what I have here is a rectangular opening, always, always, always make a picture that is 12 inches long. And it has to have the same total area. This area has to be the same total area as 2 smaller rectangular vents. One of those is 6 by 4. And one of those is 8 by 5. What has to be the width of this opening? In other words, right here, this is what's missing. I'm missing a dimension, and I need to know what this blue dimension needs to be if these areas are going to be equal. So to begin with, don't I have to know what these areas are, the smaller ones? You tell me that this is 24 square inches. Areas are always squared. Inches times inches is inches squared. We talked about that in the 6-4 section where we talked about exponents and so on. Inches times inches is inches squared. And on the other side of this thing, we've got 40 square inches. So what that says then is that the total area here, it has to equal that total. So it has to be 64 square inches, 24 and 40. The question is, how do I back out of knowing the area and knowing one of the dimensions, and how do I find the other dimensions? So if you want to see that kind of spelled out, one way to do that is to take the 64, put it in for the A, take the 12, put it in for the L, and look at that statement and ask yourself, well, how would I find the W? What do I have to do? And you'd be able to see that it means that I'm going to have to divide off that 12. To get 12W to just be W by itself, undo the multiplication by 12 so that W is by itself. I have to divide both sides by the 12, and we find then that that dimension has to be, so maybe you're looking at that and thinking, oh, it doesn't come out evenly. Did you see that? So what would we say? What would we say about that? Maybe I'm off on something here. Hold on. Oh, okay. Let's see where I am. So in the calculator, what happens with this? Let's talk about these units a little bit. In the calculator, you see that it says basically 5.3 repeating inches. Well, this is a third. In other words, this 33333 is a third of an inch. 5 1/3 inches is the actual answer to that question. 5 1/3 inches. So it's an odd unit, the 1/3 of an inch, but that's what that is exactly. We would not choose necessarily to state that in terms of that decimal and trying to round that. Wouldn't be the first choice. I'm thinking that if you saw a question like this in math lab, you'd have to look at it. I don't know whether it would be likely to ask you to give that as a decimal or to actually use the fraction. Anytime you see a 0.3 repeating, though, it means you're looking at a third. That's a third. Okay, so let's close this one and something else like that. So this one, sort of a similar context. Here we go. Similar context, square hot air duct. Square one has to have the same area as two rectangular ones. You might think, is this the same question? No, it's not quite the same question. We have a square hot air duct that has to have the same area as two rectangular ones with dimensions 6 by 4, 5 by 8. That part's the same, isn't it? 5 by 8 inches. So this is again 24 inches squared. This is 40 inches squared. So we know that what we're after is a total here of 64 square inches. This time though, instead of a rectangular duct, this thing is squared. That's the difference. And so how long are the sides then? How long are the sides of that square duct? And at that point, there's a bit of an algebra idea in there that we've talked about. If it's not clear to you what should be the answer here, what you're thinking about is what we call the square root. What is the square root of 64? If I take the square root of 64, I get the side length for the square, because 8 times 8, when I take the square root and say it's 8, that's what I'm saying is that 8 times 8 is equal to 64. So the square duct, because the side lengths are the same, then it is, and you may not need the calculator for that, but what you're thinking about is what times what, when those are the same number, what times what would give me that area. So I'm going to maybe here make up one that's just got different numbers to it so you can practice that. So let me play with that a minute. Okay, so I'm going to give some different dimensions here. Let's see. So I'll say this is, let's see, put that down. This side 3 by 7. And I'm going to say this is 5 by 2. Now I want to make that 5 by 20. So let's make the 20 on the longer side. Making this up as I go, so pardon that. All right, so let's say that one of those rectangular ducts is 5 by 20 inches, kind of an odd size, but make it work. The other is 3 by 7. This is still a square. What are the side lengths of that square duct? And so once again, I'm going to leave you to finish this one out since I did one for you like it, because I want you to be able to kind of practice that square root idea, okay? So this is in class activity day 8, number 7. Lots of these today. Okay, so you'll finish that out and specify, again, the goal is to specify those side lengths. What are the 2 side lengths there? And turn that in as an activity number 7. Okay, all right, let's keep moving then. Quadrilaterals. So specifically, quadrilaterals is not a very specific name. It simply says 4 sides. That's all it says. So you can have quadrilaterals that are, who knows? I mean, any weird configuration. You could have quadrilaterals of 4 sides that don't even have parallel sides. You can just have things that are very irregular. But a trapezoid is a specific kind of quadrilateral in that it has 2 parallel sides and 2 sides that are not parallel. So these are all trapezoids. 2 sides that are parallel, 2 sides that are not parallel. And trapezoids are kind of interesting to us because we can come up with these formulas that allow us to figure out an area, and sort of based on ideas that you don't necessarily have to understand. But what we're doing essentially is taking the 2 bases, like in this case, the 7 and the 19. We're taking those, when we add those together, those lengths, and divide by 2. If you think about that, it's an average. We're finding an average length. So we're saying that if I have a 7-inch base and a 19-inch base, making 26 total, the average length of a base is 13 inches, right? And in a sense, what we're doing is acting as if the trapezoid has become just a standard rectangle, where the top and the bottom would both be 13, and the sides here would both be 6. That's really what this is doing. So if that makes any sense to you, you can kind of store that away and deepen your understanding. But if you want to just say, no, I just need the formula, leave me alone, don't let me understand anything, I just want the formula, that's okay for now. So find the area and perimeter of this thing. We would say that the area has to be the 2 bases, as I just said. 26 divided by 2, that's the B1 plus B2 divided by 2 times the height, which is 6. So there it is, 13 times 6 is just what I showed you just now. It's sort of converting the trapezoid into a rectangle. That's a 13 by 6 rectangle. So it's at 1878. So we would say that this has an area, this trapezoid has an area of 78 square inches. Perimeter is easy, it's just adding up side lengths, no exotic anything there. It's just going to be whatever that is, 15 and 28, so 43 inches for this particular example. Perimeter is just the distance around. All right, so you'll see some trapezoid calculations in the homework. And we have here, to finish out this section, a trapezoid word problem for you. We have a cathedral ceiling in somebody's house that creates two opposite facing walls, each with the shape and dimensions shown in the figure. The homeowner wants to have a surface with textured drywall and cost of 59 cents per square foot will be the total cost for the two walls. So you will probably, without too much thought, you would probably recognize that there are a couple of ways you could do this. You could go into this as if you were going to just separate out the two figures, right? Create right angles there, and find what you'd be doing is finding the area of this triangle here, the area of the rectangle, multiplying all that by 2 because you've got two walls. You can find it that way. And some of you will go ahead and do that, I realize. Some of us would say, well, maybe I could think of this as a trapezoid. Is it possible to do this problem as a trapezoid problem? So what that might require, to make more sense of it, it might be that you would say, well, if I could turn that somehow, I could see it better. If this is the 8-foot 3-inch base, what I'm doing is pulling off the two bases that are parallel, right? The two parallel lengths are the two bases. So I have an 8-3 base. I have an 11-foot 9-inch base. And then I have the two other sides that are, again, not parallel. They don't have to be parallel. And this one would be, which measurement is that? So think about that a minute. I'm clearing this. Which measurement is that? So I'm hoping that you're saying, well, that has to be the 10'6", right? So what we've done is essentially turn this thing 90 degrees. That's really what we've done. So we have the two bases figured out, and the 10'6" is that distance that's between the two bases. It's right there. It's that 10'6" inches. And so that 10'6" is the height. It's the height of that trapezoid. So we could get this area done sort of all in one fell swoop by working with this as trapezoid rather than splitting this out as two figures. If you want to do it as two figures, you can. You might even do it both ways and see which one seems easier. The 8'3", what I'm going to do though is calculate this all in terms of inches. Well, maybe I'll do it in decimals since these are going to be even. So 8 feet 3 inches is 8 feet, for example, 8 feet and 3 out of 12, right? 3 inches is 3 out of 12 feet. It's 1/4 of a foot. 3 inches is 1/4 of a foot. So I'm going to call that distance 8.25. In other words, I can get away with using the decimal here because these will come out to be even terminating decimals. 8.25 is an exact equivalent of 8 feet 3 inches. I'm not going to introduce any rounding error. So that's my first base. Second base then, that 11'9", what can I say about that? 11 feet 9 inches. Well, 9 out of 12. Think about that. 9 out of 12 as a fraction reduces to 3/4. So this is actually 11.75 feet. Again, I can get away with using the decimal because 75 hundredths of a foot is the same as 3/4. 9 out of 12 inches is exactly 3/4 of a foot. So I haven't introduced any kind of error at all. There's no rounding or anything involved here. And in a similar way, that's 6 inches. 6 out of 12 is half a foot, right? So I could say that my height is clearly 10.5 feet without doing any damage whatsoever to my precision. And at that point, then, if I roll through this in terms of my trapezoid calculation, I know this has to be 8.25 plus 11.75 divided by 2. That's taking the average of the two bases again, and then multiplying by the height, because at that point I'm treating this as if it were a rectangle. And so, having done that piece, maybe you're working with me on these calculations. We have 20 over 2, right? Here. So this first piece is 10 times the 10.5. We work in the parentheses there. 8.25 plus 11.75. That makes 20. 20 divided by 2 is 10. So 10 times that 10.5 just means move the decimal over 1. I have 105 square feet in one wall. 105 square feet in one wall. So I'm going to kind of make a note of that right here. That's just one. So I can make a little room here. I did give you on your notes, if you want to sprawl a little bit, another space there below. So you've got room if you want to keep some of this, write some of this somewhere else. So I have 105 square foot for one wall, which is 210, of course, for the two. 210 square feet times what? Well, again, unit multiplier is a useful way to make sure I'm keeping things straight. 59 cents per square foot is that unit multiplier. 59 cents and 1 foot squared are, so to speak, the same quantity or equal. And I'm canceling my feet squared. I don't have any kind of ambiguity about whether I would multiply or divide. You might say, well, I would know that it's the cost. So it's the 210 times the cost per square foot. But again, it's a good idea to practice this because you will find sooner or later that you'll have calculations where you're going to be confused about whether you need to multiply or divide. And this is the way to keep that straight. So it's a good idea just to practice it as we're working. 210 times the 59 gives us 123.90. You can drywall the two walls for $123.90. All right, and that is the end of 8.2. So I will let you go. We'll see you on the next Tuesday evening. If you have questions on the homework, get hold of me. Good luck, and I'll see you on Tuesday. Thank you.